Hi, in this short video, we will be learning about the mid-infrared observation. Mid-infrared is the wavelength range corresponding to roughly about 5 micron to about 30 micron. And considering the Been's displacement law, any object that actually with few hundred degree of Kelvin, the temperature will radiate brightly in the wavelengths. Okay, and the front picture is actually showing the optical image of the Orion constellation versus the mid-infrared view of the Orion the constellation region, and we can see that actually there's a really bright object that actually they're coming from the tip of the dagger, and that's the giant the Orion molecular cloud, which is actually the star forming region, currently forming about millions of young stars. Okay, so in the in the infrared, especially the mid infrared, why that actually that should we worry about or they consider mid infrared of the astronomy, because the mid infrared, especially even compared to the near infrared, we can actually see cooler object. Okay, which means actually in the newborn star, which is actually still surrounded by its natal cloud, or we can actually even study that actually interstellar dust. On this upper left, the corner picture is the optical the image of our Milky Way galaxy, and toward the galactic plane we can actually see the dark the vein, and then this dark the blocking material is the layer of interstellar cloud, and interstellar the cloud actually contains the lots of dust. Okay, so this dust the blocking the light from the background, so that's why they appear black. But these dust the grains are actually the about 100 degree of Kelvin, or maybe slightly cooler, so that actually they radiate sorry, they radiate reasonably brightly at the mid-infrared, as you can be seen on these the lower right corner images. This is the mid-infrared view of the Milky Way galaxy, and the contrary to the optical the view, we can see that actually glowing interstellar cloud. Okay, and also that actually that the nebulae structures are actually bright in the mid-infrared. So the at mid-infrared the wavelengths, we start to seeing brand new type of object, okay, which can actually provide the different astrophysical insight about the nature. So that's the one reason, and then another reason is because actually that at the long wavelengths mid-infrared, we can actually see through the intervening material very well. So these two images, optical image and the mid-infrared image of these two, the Milky Way plane is a really good the example. So basically this the infrared view is actually we are seeing very close to the galactic center of our Milky Way galaxy. Okay, but in this optical view, because of the intervening blocking the dust, we cannot actually really see toward the galactic center. So this is called the interstellar extinction, and this interstellar extinction is expressed in as a symbol of A, and it's a function of wavelengths. Okay, and this is actually the amount of the extinction is measured in magnitude. So the visual extinction, this relationship is actually shown as the extinction at different wavelengths normalized against the visual band extinction. Okay, so as we can see that actually this is the 1 over wavelengths. Okay, so this side is actually the short wavelengths, okay, and this side is the long wavelengths. As we can see that actually that the extinction compared to the visual extinction is getting really small. So that means actually we can see through materials, right? Because the extinction is small, we can see through the materials at the long wavelengths, and then that change of the relative extinction is drastic. So compared to the visual wavelengths, the visual wavelength is around here, right? And that the K band, the extinction is around here, and that difference is actually just huge. So in terms of the magnitude, say that actually we put the same brightness object at the center of our Milky Way galaxy, okay, then the seeing that light that actually just traveling through all these intervening materials at visual band, we actually see 30 magnitude of extinction when actually that light reach to the Earth. At the K band, that actually the amount of extinction is only 3 magnitude. That difference is 27 magnitude of difference. Remember that actually every 5 magnitude is the factor of 100, right? So that difference is actually that, meaning that almost 100 billion times different brightness. So meaning that actually we at K band, even at longer wavelengths in mid-infrared, we can actually see through any of the intervening materials. So why mid-infrared? We actually can see brand new type of object, and because of the low extinction, we can see far. Okay, that's the main reason that why we are observing mid-infrared wavelengths. And Wien's displacement law said that the object with 100 to about 600 degree will peak its emission at the mid-infrared wavelengths. And sadly, that any of the component of the ground-based telescope. So if you think about that, the telescope are actually kept at the room temperature, and that room temperature is what, about 290 degree Kelvin. They basically radiate really strongly right in the middle of the mid-infrared. Okay, so because they're actually at these mid-infrared wavelengths, everything that actually surrounding us actually glow really brightly. So it is really tough to see through this glowing background and then detecting very faint object from the night sky. Okay, so there's a trade-off between the space telescope versus ground-based telescope. Remember that the largest this infrared space telescope that actually we sent to the space is a Spitzer telescope, and the aperture size is barely 1 meter, right? And compared to that largest ground-based telescope is about 10 meter in aperture. So that means actually that because of the meter size difference, we can achieve about 10 times better spatial resolution on the ground because of the larger telescope. But ground-based telescope will be flooded by the surrounding the mid-infrared background, the radiation. If we actually put the telescope in the space, and like the next generation telescope called the James Webb Space Telescope, the meter size is 6.5 meter, I think 6.5 meter, the meter, okay, and it has the two shield. One is the sun shield, the other one is also they're blocking against the Earth's shine. But simply just deploying these two shield, the telescope can be actually kept really cold temperature in space, and that is 50 degree Kelvin. So because of this passively cooled temperature, very low temperature, its background, mid-infrared background radiation is very small compared to the ground-based. versus and that's the old name of the next generation space telescope. So NGST, next generation space telescope. That's the successor of the Hubble Space Telescope. Now they're actually officially named as the James Webb Space Telescope. The background radiation difference between the JWST versus ground is almost 1 million times of difference. But we need to actually to achieve the large spatial resolution, we need to actually use the larger telescope. But sending the larger telescope to the space is costly, so there is a trade-off. So the mid-infrared observation oftentimes actually done from with the ground the base telescope by focusing on the mainly two band, N band around the 10 micron and then Q band. These are the atmospheric window that actually we learned about in the previous lecture, right? So and then these are actually because the atmospheric window is actually they critically depend on the dryness of the air, the atmosphere, and then also the air density, the air column density. It is best to really to carry out the mid-infrared observation on a really high, at the top of the high mountains. Okay, and then there's such a that the high mountains are usually cold, so that actually the lesser the mid-infrared, the background radiation, and smaller amount of water vapor because we actually already elevated quite a lot in altitude, and hence it is drier. So that the good place, two best the places in the world for such an observatory is the Hawaiian, the Mauna Kea, the mountain, and the Chilean, the Andes, the mountains. Okay, that's why they're actually the largest telescope in the world are built around on these two the site. Okay. Then background signal is actually mainly due to the water vapor I talked about. Okay, so the sky noise is the main the main limiting factor for usually the near infrared observation. But for the mid infrared, not only that actually sky noise, we need to actually worry about the telescope noise, because the telescope mirror is also shine brightly in mid infrared, and the support structure such as the telescope tube and secondary mirror holding the spike or the vane, and any of the instrument covers and whatnot, anything that actually light that actually just touches, right? That actually anything that actually light touches, they're kept at the room temperature, so they glow really brightly. Okay, so best the case is actually keeping everything cool, right? So by using maybe liquid nitrogen or something, but practically that creating that huge the dewar to cool everything, including the telescope, is impossible. Okay, so that astronomers are actually using very special technique to really eliminate somehow that actually just the flood of the mid-infrared background radiation. Okay, so that let's just learn about that special observing technique. Okay, so this technique is actually hinged upon the special movement of the secondary mirror. So this is the secondary mirror. Okay, and secondary mirror is actually sitting on some of the rocking the platform, and this rocking platform is actually just making the secondary mirror actually tilt every now and then. Okay, so the chop A, I will explain that actually why that actually we are using the term chop. So this is the normal position. Okay, and then why that actually that the telescope and then secondary mirror is actually the pointing to your main science target, that's the normal pointing direction, which is indicated as a chop A. Then all of a sudden that actually secondary mirror is actually tilt, okay, with a small angle. because of the tilted angle, that actually the viewing direction of the telescope is actually just moved. So now that actually you are all of a sudden that actually that you are looking at this direction, telescope didn't move, but actually only the secondary mirror tilted, then you are actually looking at this part. Okay? Why they're actually just doing this, the secondary mirror tilting? Because that remember that actually that how fast that actually that the mid-infrared sky is changing, it's in a matter of just fraction of a second. So to really the subtract this really the brightly glowing mid-infrared sky in a less than a fraction of a second, we need to actually just they observe this chop A direction versus chop B direction, A and B direction multiple times in a second. Okay, so to do this, secondary mirror is actually rattles. So basically, secondary mirror is rattles few times a second. So they're actually just rapidly changing between chop A, the direction of A and the direction of B, and then taking that actually that co-added frame. So basically, in a sense, that actually that the non-destructive readout frame at the position A and then position B, and multiple that actually the rattling, that actually we can they obtain a different image between the position A versus position B. Doing this fast enough, so typically about few times per second, about 3 hertz, we can actually that subtract the really bright background mid-infrared, the background sky before that actually change. Okay, so that's why that actually that the secondary mirror is actually just doing this actually rattling motion. That rattling motion is actually known as, I think somehow that actually astronomers is using the term called chopping the secondary mirror. Okay, so this chopping is doing few hertz the frequency, so that actually we can really subtract really bright the mid-infrared background before it is actually changing. Okay, so that idea is actually straightforward and then neat. But the problem is actually because that actually the secondary mirror is changing from chop A the position versus chop B. In fact, actually that the secondary mirror, the area that actually secondary mirror is actually seeing on the primary mirror side is actually not the same. It's slightly shifted. So that is actually that illustrated in these two beam passes. One is the orange beams. That's the regular normal the A direction. Then when the actually secondary mirror is chopped, then now that actually we are seeing that actually this cyan, the light curve. I think cyan, the light path. So as you can see that actually that area that actually that they chopped, the secondary mirror is seeing is actually slightly shifted. So that means actually it sees a different amount of imperfections, such as like the different defect, the dust rings, and different the reflection, the emissivities, whatnot. So that actually that this chop A and then chop B, background light is actually not perfectly subtracted out because of this difference. Okay. So if there is no difference in the beam path, then they're doing this fast, the chopping secondary mirror, and then we do this the chop A minus chop B, the operation, then this background light is actually really subtracted out. Okay, and doing this chopping, real object is actually also moved in two different locations, right? So then we will actually have the one positive image of the target and then one negative the image of the target. So then we can actually really eliminate the background light really good, neat. Because of this different the beam path, that the subtraction is not perfect. There is a residual. How do you actually just then compensate for these different the area of the primary mirror being seen for the chop A and then chop B position? every now and then we basically just move the telescope a little bit. Okay, so slew is actually a large movement. It is actually they call the small the movement of the telescope, so that actually the telescope is moving much slower than the chopping frequency, but actually doing basically this nodding. So the nodding the telescope in a sense that actually that every now and then, this is the typical case is actually the every 10, roughly about 10 chopping, the telescope is actually just the pointing from normally that actually that the A direction to the B direction. Okay, so for the nod A, the normal your object is actually in the vertical direction, so that's the your object is actually toward the, I think it's seen in the chop A beam. So at node one, in one node position, doing multiple chopping, then the telescope is actually moved in such a way that actually now that actually your object is seeing at the chop B position, then doing this multiple chopping. Why we are doing this? By arranging in such a way that actually that this, the nod and then chop pair of movement, we can actually so-called doing the double differencing. So chop A minus chop B in a given node position, that difference image is subtracted one more time for the nod pair. So the illustration is this. This is the chop. At node A, chop A and then chop B. This is node B, chop A and then chop B. So that's the chop at this difference the images. Okay. Then this chop difference image is again that actually that they subtracted each other. Then what we can see is actually that twice bright the positive image, and then they have the brightness negative images. And in this case, that actually any of the background, the glowing, the background at mid-infrared are actually perfectly they subtracted out, near perfectly. So this is the real example. So individual the node frame. So this is node position A, that's the node position B, and this is the chop A. So that actually your target is on the chip, and then chop the chop B, then your object is actually off the chip, and likewise. So in this individual the chop image, the background, like the sky is actually so bright. Background sky, in this case that actually I'm including that actually background, okay, including the emission from the sky actually, and also telescope, the surrounding, and then any of the environment. Okay, so in this single chop image, the recorded intensity is almost 800 million, okay, electrons. From a single chop differencing, that actually we eliminate almost few hundred times of the background images, okay, background the radiation. So from the single the chop differencing image, that actually background is actually reduced by almost 200 times, the 300 times. Okay, then doing the second the double differencing, okay, we can actually eliminate another few hundred times of the background level, so that actually the overall this so-called double differencing, the imaging I think technique, we actually decrease the background. So we decrease the background by almost 100,000 times. So in this way, they're actually doing this so-called chop and then nodding the operation of the telescope. So chop and the nodding operation, sometimes actually known as the beam switching, is because actually that in the nod A, the chop A is on the target. Now that actually after the second the nod, the chop B is on the object. So it is actually this beam is actually switched every node position. So this type of the observation is either known as chop and nod operation, or especially that actually nodding in the same magnitude and then in the direction of the chopped direction is called beam switching mode of the observation. So beam switching mode of mid-infrared observation is specific, unique to the mid-infrared of the observation, and it's the purpose is actually subtract this huge bright the background glowing at the mid-infrared, so that as you can see really faint the science target from the night sky. Okay? And this is the real example that from my own science, that actually this is the image taken with the Gemini 1000 mid-infrared instrument, and this sadly that actually this is called the T-Rex, the instrument. This was actually decommissioned almost 10 years ago. Okay? So it has the 16 readout channels, so that as you can see 16 vertical stripe. This is the typical the fixed pattern noise. Okay, and this background is actually several 100 million electron level. And even if that actually I observed one of the brightest object in the sky as a calibration or standard the star, in a single chop image, that brightest object in the sky is not even visible, right? So when I actually do the chop A minus chop B, now that actually I can see that actually that the bright star that actually I can see. Okay, then doing this the double differencing images. So the chop A and basically this is the double differencing. Okay, so at this level, right? So double difference image, now that actually I can see that actually background is nicely subtracted out. I have positive image in the center, and then maybe that actually the tail of the actually negative image on the both side. Okay, you can see that actually in here that actually that limitations of this chopping the secondary mirror. This the T-Rex, the measurement and then operation of the chopping the secondary mirror at the Gemini 1000 telescope was state of the art level. Okay, so the Gemini 1000 was actually achieving the best operation, the precision. Yet that actually that this direction is the chopping direction. Okay, you can see that actually there is a tail. The target is supposed to be just perfectly around point source, but you can see that actually there's a tail in the direction of the chopping direction. So meaning that actually that telescope, the secondary mirror is actually just fluctuating, rattling quite a lot, and that actually that the settling time is actually not achieving long enough, so that actually that there's a tail of the chopping operation. So that actually it is ruining or degrading the imaging the capability of the observation, and at the cost of actually removing huge background mid-infrared of the radiation, right? So because of this, that actually the theoretically diffraction limit at the mid-infrared is much easier to achieve, because the diffraction limit is the diffraction limit is the lambda over d. So that's the observing wavelengths divided by the primary aperture, right? So that means actually for the given imperfection, size of the imperfection in the primary mirrors and then any of the instrument surface, that the achieving the diffraction limited imaging capability at mid-infrared is much easier. But because of this special operation mode of chopping the secondary, the image quality is actually greatly degraded. So how do you actually then achieve the near diffraction limited imaging capability while they're actually just subtracting this huge the glowing of the background radiation at mid-infrared? It is actually that new very clever design is actually using the so-called adaptive secondary mirror. Okay, so the two images is the example of using the adaptive secondary mirror. So without using the turning on this adaptive secondary mirror, that's the image on the left. So you can actually see that it's still that decent. The central the object is the single star, and then there's a companion. Still, there actually we can see some hint of the first airy ring. So this is actually decent. Strand ratio of maybe close to 40% ish. Okay, so this is actually quite good. But once we actually turn on the adaptive secondary mirror, then we can actually see that actually nearly close to the diffraction limited imaging capability. We can actually see that actually 1, 2, 3, 4, even 5 airy rings. And in this case, the actually strand ratio is nearly 98%. The theoretical perfect diffraction limited imaging should have the strand ratio of 100, the 100%, right? So the strand ratio of 1. But actually this is actually already that actually achieving strand ratio 0.98. That's the remarkable. Okay, this was actually done and then they achieved by using the adaptive secondary mirror. So the homework that I'm assigning is just Google and then search on the internet about the adaptive secondary mirror and write a short the report. And this short, how short? Just a paragraph. Okay, so maybe 2 or 3 sentences long. And tell about, I think the say about the what is adaptive secondary mirror is and then what the maybe actually very short operation mode and what advantages that actually we can get, okay, by using the adaptive secondary mirror. In short, adaptive secondary mirror is the adaptive optics instrument at the mid-infrared, and basically that actually because we cannot cool all those the warm optical element that actually appear in the conventional the adaptive optics instrument, we actually have to minimize the number of optical element. So basically we are replacing the solid secondary mirror with the deformable the secondary mirror. Okay, so just Google for or just search in the internet about the details about the adaptive secondary mirror and submit the homework. Okay, so this wraps up the mid-infrared the astronomy lecture.